All right, let's get into it. The internet. We use it pretty much every second of every day. But how does it actually work? We are going to pull back the curtain and follow one tiny message on its absolutely incredible journey across the world.
No, really, think about it for a second. You tap out a message on your phone, hit send, and in less than a heartbeat, your friend on the other side of the planet sees it. It feels like total magic, right? But it's not. It's actually one of the most amazing and complex systems humanity has ever built.
So for this explainer, our hero is going to be that one little hi message. We're going to follow it step by step from the moment it leaves your screen through all the wires and routers and radio waves, all the way to its final destination. We'll see exactly what it has to go through to get there.
So, first things first, we have to tackle the biggest question of all. What even is the internet? Let's get a really clear picture of what we're talking about.
You know, this is probably the best way to think about it. It's not some fluffy cloud up in the sky. It's not one giant supercomputer somewhere. It is, for all intents and purposes, a massive global system of digital roads and highways. And our little hi message, it's like a car that's just about to merge onto the freeway.
And here's the key idea. It's a network of networks. See, your home Wi-Fi network connects to your internet provider's bigger network, which then connects to these giant regional networks, and so on, all across the world. The only reason this whole thing works is because everyone has agreed to follow the same set of rules. We call those protocols. And they all run on physical hardware, cables and routers.
Okay, so your phone doesn't just scream hi into the internet. It's way more clever than that. It actually breaks your message down into these tiny little pieces called packets. Think of each packet like a tiny digital envelope. It's got a return address, the source, a mailing address, the destination, and inside, a little piece of your message, the payload.
So, if our packets are envelopes, well, they're going to need a very specific address to get delivered, right? This brings us to the internet's version of a global postal system.
Right, so our little packet is all sealed up and ready to hit the road. But the internet's road system is just vast. It can't just start driving around hoping to find the right place. It needs a specific target, a digital house number to aim for.
And that's precisely what an IP address is. Every single device that's connected to the internet, your phone, your laptop, your smart TV, the servers that host Netflix, every one of them has a unique IP address. It is the fundamental addressing system for the entire digital world. No IP address, no connection.
Now, you've probably seen these around. There are two main types. IPv4 is the classic one you're probably used to seeing. The thing is, we literally started to run out of them. It's like running out of available phone numbers for a country. So they came up with IPv6. It's way, way longer, which gives us a practically infinite supply of new addresses for all the billions of devices yet to come.
And the system has a really clever trick up its sleeve. The entire internet only needs to know one single address for your whole house. That's your public IP. But inside your house, your Wi-Fi router acts like a building manager. It gives out private, local IP addresses, kind of like apartment numbers, to your phone, your laptop, your game console. It's a neat way to keep your home network organized and save those precious public IP addresses.
Okay, so our packet has an address. Now for the next big question. How is it going to travel? Does it need to be super careful, every piece tracked and guaranteed? Or does it just need to get there as fast as physically possible? This choice is absolutely crucial. So the two main ways to send data are called TCP and UDP. And this choice really gets to the heart of how the internet works. Do you want perfect reliability or do you want pure, raw speed? Think of it like this. TCP is like sending a registered parcel with tracking. You get a confirmation, you know it arrived, and it all comes in one piece. UDP, on the other hand, is more like shouting in a crowded room. You just yell the information out really fast and hope most people hear it, but there's no guarantee. Now, for our hi message, we absolutely, positively need every single packet to arrive, and in the right order. You can't have the message show up as IH or have the H part go missing entirely. That's why things like text messages, emails, and especially online banking depend on the slow but steady reliability of TCP. It makes sure everything gets there perfectly. So why is it a bit slower? Well, it's because before TCP sends any of your actual data, it does this little dance called the three-way handshake. It's basically a quick, polite conversation. Your device says, "Hey, you there?" The server says, "Yep, I'm here and listening." And your device says, "Great, here comes the data." This little check makes sure the connection is solid before anything important gets sent.
But what about something like a Netflix stream or a Zoom call?
In those cases, speed is everything. A tiny bit of lag is way more annoying than a single pixel being off for one frame. So they use UDP. It skips the whole handshake thing and just starts blasting data packets. If one packet gets lost along the way and it represents just one frame out of 60 in a second, who cares? You'll never even notice. The priority is just to keep that stream moving.
So we've got our packet, we've got an address, and we've picked a delivery method. Now, let's look at the full, detailed map of this journey. Every single step our little message takes just to get out of your phone. This map is called the OSI model. Now, I know it looks super technical and complicated, but just think of it as an assembly line with 7 different stations. Our high message starts at the very top at station 7, and as it moves down the line, each station adds a new wrapper or a new label, getting it ready for shipping.
So here's how that assembly line works for our message. It starts at the top. Layer 7, the application layer. That's you actually typing hi into WhatsApp. Then, layer 6, presentation, encrypts it for security. Layer 5, session opens up the connection. Then layer 4, transport, wraps it in that reliable TCP packet we talked about. Layer 3, network, slaps on the destination IP address. Layer 2, data link, puts it in a format for the local Wi-Fi. And finally, layer 1, the physical layer, converts the whole thing into an actual radio signal. Woo!
Okay, that entire 7-layer process sounds incredibly complicated and honestly kinda slow, right? Well, let's put it all together and see what this journey actually looks like in real time.
So boom, in a flash, your phone runs through that whole 7-layer process. Your router grabs the packet and forwards it to your internet service provider. From there, it hits the global backbone, these massive fiber optic cables crisscrossing the oceans, and zips its way to a WhatsApp server. That server immediately finds your friend and forwards it to their phone, where that entire 7-layer process happens again, but in reverse to unwrap the message. And here is the most insane part. The total time for that entire journey, across the country or across the world, through all 7 layers down and all 7 layers back up, is about 2/100ths of a second. It is an absolutely mind-boggling feat of engineering that we just take for granted every single day.
So at the end of the day, what are the big things to remember? First, the internet isn't a single thing, it's a global network of networks. Second, IP addresses are the essential house numbers that make it all work. Third, we choose reliable TCP for things like texts and fast UDP for things like streaming video. And finally, the whole thing is guided by that 7-layer map, the OSI model.
The fact that these billions of packets are all following these incredibly complex rules and they find their way to the perfect destination almost every single time, it's really nothing short of a modern miracle. But it does leave you with one final thought. With so many intricate moving parts, what happens when just one of those tiny little steps breaks? Well, that's when things get interesting.